Good morning, dear student. In today's lecture, we discuss the wacker process. So, we are very much familiar with this process, that is wacker process. So, conversion of this carbon-carbon double bond, that is conversion of alkenes to aldehyde with the help of PD second as a catalyst, is known as wacker process. So, what is this wacker process? That is conversion. So, if you consider the alkene is there, and in presence of PdCl4 2 minus means the PD is in plus 2 oxidation state, and in presence of water the alkene is get converted into aldehyde, acetaldehyde. So the wacker process is used to produce acetaldehyde from ethene, carbon carbon double bond, and oxygen, that is we can write here also. This reaction can be written as CS2 carbon carbon double bond in presence of O2, one half O2, and it convert into this CS3 uh, C double bond OH. So alkenes in presence of one half O2 and PdCl4 2 minus. So in this case, this PD it is in plus 2 oxidation state. This PD it is in plus 2 oxidation state, and this PD, the actual oxidation of this alkene, it is carried out by ethene, that is whenever C2H4, that is your carbon carbon double bond ethylene, it will react with your PdCl2. So in this case it is PdCl2. This PD it is in plus 2 oxidation state. Then the ethylene is converted again in presence of water. So the wacker process, conversion of alkenes into aldehyde in presence of 1 half O2 and water. So initially the ethylene, the actual oxidation of ethylene is takes place with the help of this PD second in presence of water, and the conversion of this alkene into aldehyde with a reduction of this PD from plus 2 oxidation state to 0 oxidation state plus twice HCl. And this is the inactive form of the catalyst. Inactive form of the catalyst, because whatever the catalyst which is used in this wacker process is the palladium, it is present in plus 2 oxidation state. So whenever there is a conversion of alkenes into aldehyde, the palladium get reduced to PD0 and it is inactive. So again, to convert this PD0 into PD second, we used a second catalyst, that is you use a second catalyst, that is copper. So copper second is used, that is to convert this PD second, or to convert this PD0 into PD second, we required a catalyst, that is copper catalyst CuCl4 2 minus. So in which again the copper it is in plus 2 oxidation state. The copper it is in plus 2 oxidation state. So whatever, after conversion of one molecule of alkenes into aldehyde, the PD is converted into PD0, that is it get reduces, and again you have to reoxidize this PD0 into PD second with the help of copper second as a catalyst. Copper second as a catalyst. When this PD0 is converted into PD second, then what happen? This copper, that is PD0 is converted into PD second, and the copper second is converted into copper first. This copper second it is converted into copper first. So the oxidation of this PD0 to PD second is carried out with the help of this copper second, and this copper second, when there is a oxidation of this PD0 to PD second, it will get reduces to copper first, and the copper first which is obtained, it is again converted to copper second with the help of oxygen, then with the help of acid, that is HCl. So whatever the copper first So this is the reaction. So initially first, the general reaction is the conversion of alkenes into aldehyde with the help of PD second as a catalyst. PDCl4 minus is the active catalyst. Actually, the oxidation of this alkene, it is carried out with the help of this PDCl2, that is PD in plus 2 oxidation state. We can write PDCl4 minus or PDCl2 to show the palladium in plus 2 oxidation state. In presence of water, the alkene is converted into aldehyde. At that time, this PD get reduces to PD0 and it is inactive form. So again you have to convert into its active form. We require second catalyst, that is CuCl4 minus copper catalyst, in which copper is in plus 2 oxidation state. So with the help of this catalyst, we convert this palladium 0 into palladium second. That is, again we reoxidize the palladium uh, in plus 2 oxidation state, that is conversion from PD0 to PD second. And what happened at that conversion, the copper second is get reduces to copper first. Again, for the effective conversion of PD0 to PD second, we require copper second, and therefore the copper first is again converted into copper second. Copper first is again converted into copper second uh, with the help of oxygen and acid. With the help of oxygen and acid. So what happened? This copper first is again converted into copper second. This copper first is converted into copper second. But at least you should know what is wacker process. That is the conversion of alkenes into aldehyde with the help of PD second as a catalyst. The actual oxidation is takes place in presence of PD second, and there is a conversion of alkenes into aldehyde, and the PD get reduces to PD0, which is inactive. The inactive PD0 is again converted into active PD second with the help of copper first. So what happens when there is a conversion of PD0 to PD second, the copper get reduces to copper first, and again with the help of oxygen and acid we can convert this copper first into copper second. So let us discuss the catalytic cycle or different processes of this wacker process or wacker cycle. It is also known as Smith process. Okay, so let us discuss this process or the cycle. That is the first step. If you consider, this is the first step. That is, if you consider the first step, that is substitution. It means the PD, Cl, 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 PDCl4 minus ion. So it is your 16 electron species. PD, it is a member of nickel PDPT. So it has valence electron, 10 valence electron. The total for chlorine is there 14 and minus 2 charge. So total 16 electron is there. So first step is the substitution of one of the chloride ions, that is Cl minus ion, by carbon carbon double bond alkenes. So substitution. So elimination of Cl minus, and what you get here, we get this, that is PD Cl Cl Cl. This is carbon carbon double bond, that is alkene is coordinated, and we get here a negative charge. So in this case, we count the electrons. That is, we know that this alkene, it is a 2 electron donor, and therefore the chlorine is not removed, the chloride ion is removed, means Cl minus. So Cl minus, we know that Cl minus is 2 electron donor. So if we count the electron again, in this case PD has 10, then it having the alkenes having 2, that is 12, 13, 14, 15, and to make the electron, to make the species 16 electron, there must be a minus 1 charge. So it is also 16 electron species. So this is the first step in wacker process. That is, whatever the PDCl4 minus, there is a elimination of the chloride ion, that is the replacement of chloride ion by alkenes, carbon carbon double bonds. Again, in the second step, if you consider the second step, that is one more chloride ion is removed from this uh, 16 electron species, which is formed with the help of water. That is the removal. So in second step, PD, Cl, Cl, Cl. This is alkene is there, it having a negative charge. Again there is a removal of Cl minus, so another Cl minus is removed with the help of water molecule. So in this case, in the first step, the alkene is coordinated to the palladium, and in this case the water molecule replace one of the chloride ions. We know that water molecule is also 2 electron donor, that is the oxygen having lone pair, so it is a 2 electron donor, and therefore there is a removal of Cl minus ion. There is a removal of Cl minus ions, and we know that the trans effect of this alkene, that is the trans effect of this alkene is more as compared to this chloride ion, and therefore the chlorine which is trans to this carbon carbon double bond get removed or get replaced by the water molecule. And what you get here, you get here PD, this is your water, this is your alkene, and this chlorine is there, chlorine is there. And if you count the electrons, so in this species, in this wacker process, there is no conversion of 16 to 18, 18 to 16 electron species, so all species are 16 electron species. So if you count this, it is also 16 electron. And if you count this, this PD, it is 10, then chlorine is 2, 12, then this 2, 14, and this water molecule is 2 electron donor, therefore it is 16 electron species, and there is a no charge on this species. So this is also 16 electron species with elimination of Cl minus, with elimination of Cl minus. And in this case the water molecule act as a 2 electron donor, the water molecule act as a 2 electron donor, the water molecule act as a 2 electron donor, so we get this species. So the first step is elimination or substitution of one chloride ion by carbon carbon double bond, that is alkene. And in second step, the substitution of trans chloride with respect to carbon carbon double bond by water molecule. So this is the second step. Let us discuss the third step of this wacker process. In the third step, so we get this, that is PD, and then there is a water, then there is a carbon carbon double bond is there, one of the chlorine is there, and another chlorine is there. So this is the species, and it does not having any charge. So what happened, the next step, the water molecule, that is water molecule, it will attack on these coordinated alkenes. So why this water molecule is attack on this coordinated alkene, because we know that the coordinated alkene, it is electrophilic in nature. So you should keep in mind, that is the coordinated alkenes means the alkenes which is attached to the metal atom, it is electrophilic in nature. So coordinated alkene is electrophilic in nature, and therefore this water molecule act as a nucleophile, and it will attack on this electrophile. And what happen, due to this, when this water molecule attack one of the carbon, then the hepticity of this carbon carbon double bond, it decreases, and the hepticity 2 is converted into 1 by the attack of nucleophiles. So nucleophile is attack on this alkene because this alkene is electrophilic in nature. So whenever the carbon carbon double bond is attached to the metal atom, it is electrophilic in nature, it is electron deficient, so it is act as an electrophile, and therefore nucleophile can be attacked on this carbon carbon double bond. And what you get here, so in this case we see the water molecule is attacked on one of the carbon, and the hepticity 2 is converted into hepticity 1. So what you get here, so we get this, that is PD, water, chlorine is there, chlorine is there, this is your ch2 and this is your OH having positive. So to neutralize this charge, we can write this structure as PD, and the complex, to write this as like this, Cl, Cl, cs2 cs2 OH. So to remove the charge on this oxygen, we can write this as CS2 and this complex must have a negative charge to become 16 electron, because it is 10, 11, 12, it is 13, it is 14, 15, and one negative charge. So this is your 16 electron species. So this is the step. That is in the third step, after dissociation of two chloride ions, one of the water molecule, it will attack on this coordinated alkene, because this coordinated alkene is electrophilic in nature. And what happened due to this nucleophilic attack, the hepticity 2 is converted into hepticity 1. Hepticity 2 is converted into hepticity 1. And to make the species 16 electron, we write a net negative charge, one negative charge on this complex. So we get this, that is PD Cl2 water CS2 OH. This is the third step. So let us discuss the fourth step. So what happened in fourth step? Let us discuss it. In the fourth step, that is we get this PD, then one water molecule is there, chlorine is there, and we get this, that is CS2 OH is there, and it having a negative charge, this is the species. This is your fourth step. So what happened at this step? So if you see the mechanisms, we can write this as we can write this complex as like this, that is PD. Okay, here Cl, this is your water molecule OH2, and this is your like CH2, and this is your CH2, and this is your OH. We can write this as OH. So this complex is written as like this. Okay, so what happened in this case? The lone pair of this oxygen, so same molecule is written as in this fashion, that is PD having two chlorine, one water molecule, and the CS2 OH, to understand the mechanism. So what happened in this case? The lone pair of this oxygen, it will attack on this one of the hydrogen, it is shift, that is hydride, as a hydride it is shift, and the bond get break. So what you get in this case, that is we get this, that is OH having positive charge, then this carbon, this having hydrogen, and here after removal of this hydrogen from this carbon again, and it's attached to this carbon, that is we get here CS3. And what happened in this case, we get here PD, okay, having Cl one water molecule, and there is a net negative charge, so there should be a -2 charge on this species. And we can write this as, okay, to remove this charge we can write this structure as like this, that is CH3H C double bond O CH3. So we get our aldehyde, that is we get this aldehyde, because to neutralize the charge we can write this. Okay, so what you get here, CH3 C double bond OH, and we get this species, that is PD Cl2 OH2 2 minus, in which the PD it is in zero oxidation state. So if we count this oxidation state, that is -2, which is equal to -2. So if you count this oxidation state, that is the chloride having, water is a neutral ligand, the chloride having -1 charge, so -2, which is equal to -2. So -2, it becomes +2, so it becomes 0. So this is the case. So here -2, because of 2 chloride ion is there, the net charge is -2. So -2, this -2 get transferred to right hand side, it becomes +2, and the net charge is 0, and therefore this PD it is in zero oxidation state. And to convert this PD again into PD second, so the conversion of PD0 to PD second is carried out with the help of copper second as a catalyst. So what happens when there is a conversion of PD to PD second with the help of copper second? The copper first, that is copper second, is get reduces to copper first. So copper second get reduces to copper first. When there is a conversion of PD0 to PD second, copper second is converted to copper first, and we get our the product, that is aldehyde. So this is all about the wacker process. Okay, the conversion of alkenes into aldehyde. In the next lecture we will discuss the remaining part of this chapter. Thank you.